journals, but archive versions, and then later you see being continued throughout. Definitely,
That's great.
Good stuff. Okay, let me just make sure that my iPad is going to respond. Okay, it made sounds. That's good. It's a good sign usually. Ah, there we go.
Yeah.
Okay, great.
Great, Paulette. Very well. So let's start. So good morning, everybody, to this third lecture on dark matter. Today, Unity is going to speak about dark sectors. And so go ahead, Unity.
Okay, thank you so much. Good morning, everyone. Welcome back. So we're going to start our third lecture of this lecture series, third out of 4. And the topic we're going to be talking about today are dark sectors. And so what we've seen so far, let's just sort of recap. We've developed together several mechanisms, and we've understood the behavior, we've understood what type of interactions are responsible for dark matter in each case, and what size of the cross-section would be we'd have to have in order for these ideas to explain the observed dark matter relic abundance. And we've also seen how that translates into couplings versus masses and relationships between them, and how it changes as we change through mechanisms. So let's just write that out. We've developed several mechanisms, and we've understood the behavior. And we've seen then values of M and alpha and the relationship between them. And so far we've kept it really at what I called the mechanism level. And what I want to just show you today, and this is sort of usually the next step that one would think of doing, is to move it now towards models, to do some model building. Okay, so what I mean here by models are theories that realize these mechanisms. Okay, and so sort of, I guess, I think of supersymmetry as sort of the poster child for either the WIMP case or maybe the co-annihilations. And we saw also an example of a model. We saw that toy Z3 symmetry model when we talked about 3-2 annihilations for simp dark matter yesterday. So those are sort of some examples of models. And what I want to be able to show you guys is, until now we've written out these mechanisms, and what I want to sort of make sure to emphasize to you today as a takeaway is that these different types of mechanisms, and as we saw, there are so many, and we haven't even gone through all of them together in class. These mechanisms are really something that can happen generically in theory land. Okay. So these aren't sort of fine-tuned or super special. These are really just things that can naturally happen in theories of particle physics that we write down. So that's really something that I hope you take away from this lesson, is that these mechanisms are really generic in theory land. Okay? And so obviously I'm not going to go through every single theory, every single model that anyone could ever write down, but what I want to give you a sense of is general classes of models and how these different mechanisms come about in them. Okay, so that's our goal for today. And after we talk about dark sectors, by the way, towards the end of the lesson, we'll be also discussing general constraints on if you're ever writing down a mechanism for dark matter, a new mechanism, or new models, types of constraints that you should sort of always keep in mind. So we're sort of going to give you a laundry list of that. So that's going to be towards the end of today's lesson. So let's start with our dark sector zoo. Okay, so what exactly do I mean by a dark sector? We'll just think about our ordinary standard model. Okay, so here's my standard model. Okay, standard model. And this standard model is, sometimes we call it the visible sector, right? These are all the particles that we know and love. And we know that there is a huge zoo of these particles, right? It's not one particle, two particle. There's a whole zoo of particles So we have a zoo of particles that aren't just random, they obey a symmetry structure, right? They're governed by a symmetry structure, right? We have SU3 color or strong force times SU2 weak times U1 hypercharge. And this symmetry structure and the field content, and so the particles, the symmetry structure governs everything about how these particles are interacting with each other and all sorts of observations that we see around us. And so what I want to ask is, why couldn't our dark matter similarly maybe not just be one particle or a few particles, but really be its own dark sector? Okay, some group of particles. So let me call this here. Here's my dark sector. Okay, so why can't this happen in the dark sector too? Why not in dark sector too? Okay, and maybe this whole dark sector and all of these particles are likewise also governed by some new gauge symmetries. And so what we're going to do is sort of write down, let's try to think of what these dark sectors could be. So let's just take inspiration from the standard model. Okay, so inspired by the standard model. So let me think of what could these gauge groups possibly be. Okay, and there, of course, it could be really anything. So let's just, for instance, inspired by the standard model, maybe we have some SU3 dark. Okay, an SU3 gauge theory, a symmetry that operates on the particles in the dark sector, like some dark QCD. Okay, and in fact, it turns out it doesn't actually, of course, it doesn't have to be so similar to the standard model. I can just think of sort of generalizing this to any other gauge symmetry. So maybe there's some general SU and C dark symmetry, or an SO and C dark symmetry, or even an SP and C gauge symmetry. Okay, and so these are examples of theories, gauge theories, that could exist, or that our dark sector could follow. And maybe just like we have in our standard model, we have UN electromagnetism. Maybe there's some dark electromagnetism. So maybe there's also some UN dark. Okay, a dark electromagnetism, and this dark electromagnetism, for instance, could have so it's a dark electromagnetism. So maybe I have a dark photon. Okay, so I'll call it here a dark photon. And this dark photon can actually kinetically mix and speak to the regular photon, and that gives us a way also for these sectors to talk to each other. So maybe this is a kinetically mixed dark photon, and we'll write that out, we'll draw that out in a moment in more detail. Okay, so maybe we have some piece that's like a dark version of electromagnetism. Maybe we have some dark version of QCD, and it can even be more general than QCD. So just to sort of spell this out, all of these, these pieces over here, what I mean is that maybe we have some strongly coupled dark gauge theories. Okay, or just think of these as QCD-like gauge theories. Okay, so this is what I just mean is that our dark sector, could look somewhat like QCD, somewhat like a dark version of QED, etc. So all of these are in principle possibilities for a lot of very rich dynamics and rich content of particles and interactions that could be contributing to our dark matter. Okay, so for this kinetic, so just to make sure we all understand what this kinetically mixed hidden photon means, so it could be maybe the simplest version of a dark sector is just to take a dark version of electromagnetism, just to take a U1. So it could be that we just have this dark U1. Okay, so think of this as a dark version of quantum electrodynamics with some dark particles. Okay, that are charged under it. Okay, and what this means is, and so in terms of a Lagrangian, so we have some, basically everything like electromagnetism, but in the dark sector. And importantly, in the Lagrangian, we can also write down a term that kinetically mixes that dark photon into the regular photon. Okay, so I can have a term in my Lagrangian that looks like minus, just call it epsilon over 2. Epsilon is going to be small. F mu nu, the photon field strength, times F prime mu nu, the dark photon field strength. Okay, and I have some dark gauge coupling, call it ED, okay, to separate it from the ordinary one E, or alternatively I have some dark coupling strength alpha D. And so if you kind of think of this, what this looks like pictorially is, here's my hidden photon. So let me call this hidden photon, by the way, V. Sometimes it's also, people like to denote it by gamma D, gamma being like the photon, little index D being that it's a dark version of it. So here's, let's say, my vector V, okay? And I have dark particles that are charged under it, so they interact. Here's my chi, the dark matter, or some other particles in the dark sector. They have some charge, and the strength of this interaction is, of course, governed by the coupling strength of this dark U1. But because of this kinetic mixing term, I can also, so here's my insertion of this kinetic mixing, and I can mix into the ordinary photon. And through the photon, I now have interactions with all of my ordinary charged standard model particles, for instance. Okay, so what this kinetic mixing does, what this U1 actually gives us, is the kinetic mixing gives us dark matter standard model. It gives the dark matter standard model a way to communicate. Okay, so this is how our dark sector, for instance, can now couple to the standard model. Okay, and so looking back at this picture that we drew up here, what I mean is that there's now also some way for these two sectors to talk to each other. Okay, and for instance, over here through some interaction strength epsilon. So this is probably the simplest version of a dark sector, which is just dark QED. But of course, dark sector doesn't have to be quite that simple. And as we said, we could have additional gauge symmetries. So let's just see what that might look like. So it can also be more complicated. And so we can think of these QCD-like dark sectors. And what's important, as I was saying before, is that these are very rich theories. Okay? And if they're rich theories, rich set of interactions and particles, it's really a rich playground for many dark matter mechanisms and processes to occur. Okay? And this is something that's true in general. Anytime you write down a particular model, as I was mentioning yesterday, when we talked about the WIMP-SIMP-ELDR phase diagram, it's very often the case that when you write down a particular model, it's going to have a whole bunch. So you write down what is your Lagrangian, what is your particle content, what is your symmetry structure, and then you go ahead and just work out, okay, what are all the processes that are relevant? And it's very often the case that there are multiple processes that are occurring, and then depending on relative strength of parameters and masses, you might find that you're in a region in parameter space where one process is more important or a different process, and that will lead you to different mechanisms to set the abundance of dark matter within the same theory. Okay, so this leads you to different phases of the theory. But this is certainly going to be the case also over here. So this the fact that these are rich theory, this is something that's true in general. Let's just write that out. That in a given model or theory, we often have multiple processes that can occur. Okay, and then depending on the relative size of these different things, you might get realizations of different mechanisms that control the abundance. Okay, and certainly, so I'd call these sort of different phases of the theories. Okay, and the perfect example of this is what we saw yesterday for the case of, so the example for this, let's just write that out, was what we saw yesterday where where we'd flow from a regime where our parameter space was WIMP-like to a regime where it was SIMP-like to a regime where it was an elder in that phase diagram towards the end of yesterday's lesson. Okay, and so for these rich theories that we're talking about, if I think of sort of the particle content, so, whoops, let me change the color there, sorry. So in these QCD-like theories, just like in QCD, there's a whole bunch of particles. We have all of these crazy mesons. I mean, they're not crazy. We have a lot of mesons. And also these theories are going to have a lot of mesons. So have a whole host of mesons. If you think about in QCD, we have the pions and we have the rhos and we have the kaons and the etas, etc. So there's like a whole big bunch of these. And in this case over here, now these are going to be dark. Okay, so we're going to have some dark versions of these types of particles. And what I'm going to show, what's going to happen in these theories is that actually it's not only the case, but what you can have is that the lightest state, so of course the lightest state in this dark sector will be your dark matter, but very often it's the case that the pions, okay, where pions is sort of a stand-in in general for the pseudo Nambu Goldstone bosons of these theories, so that's pseudo Nambu Goldstone bosons, if you're not familiar with that notation, of these theories. These are usually the lightest degrees of freedom, and these can play the role of dark matter. Okay, so we're going to have some dark pions, which is what I'm going to be denoting here by pi. Okay, so these are some dark pions. Okay, so let's take a look at how in this setup, many of the processes or the mechanisms that we've described earlier in our first two lessons actually emerge. Okay, so let's look, for instance, at 2 to 2, a whole bunch of 2 to 2 processes. And so just to show you, so for instance, starting with a regular 2 to 2 annihilation, the WIMP-like process. Now I could have pions. Here are my 2 pions coming in, exchanging another pion and going into 2 vectors. Okay, so this would be the ordinary 2 to 2 annihilation that's WIMP-like, the process that is often called the WIMP. I can also have actually just an ordinary 2 to 2 annihilation like this. So in another diagram, I could have 2 pions come in, and if these are charged pions that are charged under the dark U1, then they can talk with that vector. And now the vector mixes with a photon, and through this we annihilate into standard model particles. So this would be, again, these 2 to 2 annihilations for a WIMP-like particle, for a WIMP-like process, excuse me. We can also have forbidden processes here. So for instance, I can take 2 pions and have them annihilate again through another pion and go to dark, heavier mesons, for instance, dark rho mesons. Okay, so this would be a forbidden process. And that's because in QCD-like theories, the mass of the rho is heavier than the mass of the pions. So we can also have forbidden processes that just naturally occur in these theories. Let's write down a couple of other processes that we can have that are at the 2 to 2 level. So we can also have elastic scattering processes, which we saw played an important role for the WIMP and for the SIMP as well. So let's just see over here. Okay, and this is a process that can maintain kinetic equilibrium between our dark sector and the standard model. So I can have pions that are scattering off of standard model particles, again, by going through this vector that's mixing into the photon. So this would be an elastic scattering process, which we saw is something that we need either for kinetic equilibrium, or was a process also for the elastically decoupling relics. And there's one more type of process that we can write over here, which we didn't analyze in detail, but it actually, if you were to perform sort of that back of the envelope estimate for it, you'd see that at the back of the envelope, level, the freeze-out condition is essentially identical to the 2 to 2 WIMP-like case. So, so it's very similar, but we did mention it when we listed all sorts of 2 to 2 processes. So we can have semi-annihilations where 2 pions annihilate into 1 pion and 1 vector. So this would be a semi-annihilation process. And that's another type of process that could happen in these theories. Now, the idea is that in each case, you would take down, you would take your particular gauge group, your particular particle content, and you might have these processes occurring. And then what you'd always do is you'd go ahead and compute what is the cross section, like literally compute it in terms of the parameters of the theory, and then you translate that into the cross section, into sort of the language of the generalized cross sections that we've developed together over the course of the previous 2 lectures. So that's sort of the prescription. So for each case, you can compute from whatever Lagrangian that you have. And your Lagrangian is a function of your gauge couplings and the mass of your dark pion and some decay constant of this dark pion and the mass of this vector, et cetera, et cetera. So all of the parameters of your particular theory, you go ahead and take your Lagrangian and you compute in each case the cross section that you need for the relic abundance. Okay, so you'd compute whatever thermally average cross section is relevant for a particular process. So you compute this as a function of all of these parameters. Okay, and once you do this, you can now translate this cross section. You translate the cross section that we developed previously into this model. Okay, to understand what parameters, what values of the parameters, and what relationships are needed in your model. Okay, so that's sort of the general prescription. Once I have a particular theory, I write out all of the diagrams that are relevant. I compute, I compute what are the processes, and I compute it in terms of the parameters of the theory. Of course, depending on what the parameters are, it might be that one process is more important than another. And then you can match that on to the sort of general case at the mechanism level of the cross sections that we developed in order to explain the relic abundance. And then you're no longer using some, until now we've always been very careful to write down some alpha effective, and that's because it was just a way for us to parameterize the cross section of a particular process. And here you can actually write down what is the actual cross section that's relevant, and then translate your parameters mapping onto that effective description that we've done in the past. So that's this is sort of the story for the 2 to 2, and of course it's a very similar. It's always going to be the same type of procedure. But what I want to now show you is how 2 to 2 processes. Maybe we don't have to go to such complicated or such rich theories in order to get 2 to 2 interactions, but they're certainly abundant, and there are many of them within these types of theories. What I want to show you is how you can even get the sort of maybe the oddest type of interaction that we spoke about, that might be sort of the newest one to you, which are the 3 to 2 interactions that we saw were relevant for Simpson for elders. Okay, so I want to show you how these types of theories, which are super generic, supernatural, can also give rise to 3 to 2 interactions. Okay, so that's going to be the next part that we're going to do here.
Before you make this proof, there is a question. Is the dark photon massless or massive?
It's over here. It's massive. So it can be heavy or it can be light. It's a free parameter in the theory. It could be that there's just what's called a Stuckelberg trick, and there's just a mass term that appears there. It could be that there's a dark Higgs, and there's a dark Higgs mechanism that's giving it its mass. But but I'm assuming here it does have. I mean, it could also be, if it's massless, it becomes a little bit more tricky because there are constraints on how many. If you have kinetic, if it shares the same temperature as the standard model, then there are issues with how many new degrees of freedom you can introduce in the early universe. So typically it's taken to have some mass, but its mass could be lighter than the dark matter, heavier than the dark matter, by a lot, by a little. It's in principle a free parameter in your theory.
Okay, thank you.
Okay, so let's move on to talking about, within the same theory, let's look at the slightly weirder, less familiar interactions that we discussed, which are 3-to-2 interactions, okay? So they said, in a way, these 3-to-2 interactions that we described for the strongly interacting massive particle, they might seem sort of the most exotic, quote unquote, less familiar than 2-to-2. But actually, the standard model has 3-to-2 interactions. Okay, so we're maybe not used to thinking about them, but the standard model itself has 3-to-2 annihilations. Okay, it has 3-to-2 interactions. Okay, so it happens in the standard model. And so let me show you how this comes about in the standard model. So let me give you a brief reminder of QCD. Okay, what happens in the standard model itself. So QCD, I'm going to phrase it in the following way. So QCD, oops, sorry, actually, let me write it in the following way. So what we have in this case is, in our standard model, we have an SU3 gauge theory. And it has three light flavors, right? Light quarks, the up, the down, and the strange. Okay, and so this theory has, at very high energies, before the theory confines, we have an SU3 left cross SU3 right global symmetry. Okay, so this is a separate rotation, a separate SU3 rotation that we can do for the left-handed particles and for the right-handed particles. And what happens is, as we go to lower energies, the theory confines. This is what's known as chiral symmetry breaking. Okay, so we have chiral symmetry breaking. And what happens is that these SU3 left cross SU3 right break down to only have one diagonal now, SU3. Okay, so there's only now a global diagonal SU3. Now in QCD itself, this is actually not an exact symmetry. It's only approximate because the masses of these three particles, up, down, and strange, are not really degenerate. Okay, but it's a good approximate symmetry. And what happens at the sort of at the bottom line is that this theory has 8 degrees of freedom that remain, that are the pseudo-Nambu-Goldstone bosons of these theories. So it has 8 pseudo-Nambu-Goldstone bosons, and these are the kaons, the pions, and the eta. Okay, and this is because we have 8 broken generators when we go from our SU3 cross SU3 down to our preserved diagonal SU3. And so we have these 8 pseudo-Nambu-Goldstone bosons. These are the kaons and the pions and the eta that we've measured. And this theory has 5-point interactions. Okay, it has 5-point interactions. Okay, we have in the standard model a K plus K minus that annihilates to pi plus pi minus pi naught, where these are not dark particles. These are literally the particles, the kaons and the pions of the standard model. And we have this this annihilation that actually happens in this theory through something that's called, it's a topological term that appears in the Lagrangian, and it has a name. It's called the Wess-Zumino-Witten term, or in short, WZW. And this is, in case you're interested in reading some theoretical papers about why this is called a topological term and why this term exists. I'll just tell you that this is based on work by Wess and Zumino in 1971, and then followed up by 2 papers by Witten in 1983. Okay, so these are really beautiful papers to read. And these papers showed that there is a term in the Lagrangian that has 5-point interactions. And in fact, if you would take the standard model and compute the rate for this 5-point interaction to give us some 3-2 annihilations, you'd find that it would be just right to be a SIMP if the mass of the particles was of order 100 MeV. Okay, so that is that's extremely inspiring. So just write that out. If you calculate the rate, you'd find that it's just right to be a SIMP. In other words, you get just the right size of the cross section if the mass was of order 100 MeV. Okay, and so inspired by this, we're going to be able to. Sorry, we did a blue up here. Okay, and so inspired by this, let's look at these general QCD-like theories and see what happens. Okay, so literally we're going to draw the identical analogy. So, and I can do this with any gauge group. Let me just stick to an SU. I don't have to stick to an SU3. Let's do an SUN. Okay, some general number of colors because it's just true in general. So let's say I had some SUN gauge theory with some general number. Let me call it NF flavors. Okay, so it doesn't even have to be 3. It could be 3 or more that have degenerate mass. Okay. And so this theory, before it confines, has very similar again to the QCD case. It has an SUN left cross SUN right global symmetry. And once the theory confines and chiral symmetry breaking occurs, this is broken down to the diagonal SUN diagonal. Okay. And this is actually, just to point out, this is now an exact symmetry. Okay, and that's because of the degenerate mass term that we write down for the quarks. And that's important because it will guarantee that the dark matter is stable because there's a symmetry that's protecting it from decaying. Okay, so we've literally constructed here something that that gives us stable dark matter, and that's great. So the theory confines, we now have this diagonal symmetry, and importantly, just like we had beforehand, a certain number of pions, a certain number of pseudo-number Goldstone bosons. I'm just call it in general n. It's a function. I'll call it n pi. Okay, pseudo-number Goldstone bosons. What is this number depends on the gauge group, depends on the number of colors and the number of flavors. But importantly, these are, I'll collectively call these the pions, and these pions can play the role of dark matter, okay? And just to stress this, they're massive and they're stable. So that's a great feature over here. And this theory, just like the standard model itself, has 5-point interactions in the form of this Wessel-Mina-Witten term that exists. And now let me write it out for you explicitly in terms of the parameters of the theory. So the Lagrangian for the Wessel-Mina-Witten term has the following form. So, and the numbers aren't going to be important. I just want to show you, we're going to take this as an example and sort of work through how we understand how to map on our previous results into the language of a particular model. Okay, so it looks like twice the number of colors over 15 pi squared over the decay constant of the pion to the 5th power. It's the dark decay constant of the pion. Then I have an antisymmetric tensor, epsilon, mu, nu, rho, sigma, and trace of a whole bunch of pion matrices. So it goes like pi, d mu, pi, d nu, pi, d sigma, pi, d rho pi, d sigma pi. Okay? But what's important over here to just notice from this, from the way that we've written it down, is you see I have 1, 2, 3, 4, 5 pions. Okay, and they're contracted in a particular way with derivatives. And I have a particular coefficient over here. And you see that also my coefficient is written now in terms of one of the parameters in my theory, which would be the decay constant of these dark pions. Okay, so this is the decay constant of the pions. So sorry, pion decay constant. And what you see over here is that we have 5 pions that are contracted in a particular way. Okay, so once I have my theory, I now understand what my Lagrangian looks like, And I can now take this and do some computations with it, okay? And what we've sort of spelled out over here, inspired by the standard model, doesn't have to be done just for a gauge group that's so similar to QCD. I'll just mention briefly that you can do this exact same thing for any, so we just showed it for any SU gauge theory, but you can also do it for an SO gauge theory or for an SP gauge theory, provided that you have enough flavors. So here you need at least 3. Here again, oops, you need at least 3. NF larger than 3 here, and in this case, larger than 2. But as long as you have enough flavors, this is something that you always get. And from this Wessel-Witten Lagrangian, you end up with a 5-point interaction, which is taking 3 pions and annihilating them into 2 pions and giving you the SIMP process that we discussed. And so we can, yes?
Sorry, there's a question.
Mm-hmm.
SO3 is isomorphic to SU2. So is it sufficient to have SO3 to have all these effects, or should it be larger than 3?
No, I think you can have also 3. I'm going to give you guys a reference in a moment to where you can read more about maybe a less theoretical paper, the paper that we wrote out that sort of spells this out in the context of SIMP, and then you can really see how we break down for each group. But they're different. I mean, SU2 is just like the SP2 case with 4 wild fermions, and that's the minimal case where you end up with 5 pions. So these are indeed, you can do this in general for any of these gauge groups. And if you want to read more about exactly how what is the condition, the topological condition has to do with the fifth homotopy group of the coset space, the symmetry that you had, mode the symmetry that the residual symmetry that survives. And so there's a lot of interesting group theory that goes into understanding why this topological term is there and also why it's topological. Yeah, you'll be able to read that in either the Witten papers or the references that I'm going to write down in a couple of minutes.
Okay, perfect.
Okay. Thanks. Okay, so we have this 5-point interaction, and so what we can do right now is take this Lagrangian, and as I said, now we compute the cross-section in terms of the parameters of the theory. So let's just do that right now. So let's write down what is my. So remember, for the SIMP, we had some 3 to 2 thermally average cross-section, which we denoted as sigma v squared 3 to 2. Okay, and so let me just show you. If I take this Lagrangian and compute it over here, here's what I get. It's 5 square root of 5 over 2 pi to the 5th. There's some number of colors, which I think I just called here n, not nc. So let's just leave that nc squared over x freeze out squared m pi to the 5th over f pi to the 10th. And then there's some factor here. Let me just call this some t squared over number of pions cubed. And so this piece over here, this, which I'm not going to write out, this is some combinatorial factor. That depends on, it depends on the group, and it depends on NF, etc. And we have tables of these in our paper. Okay, and so here is the 3 to 2 cross section in terms of the parameters of the theory. Okay, m pi is the dark pion mass, f pi the dark pion decay constant. So this is what we previously, just to stress this point, this is what we previously called alpha effective cubed over m dark matter, so that would be m pion here to the 5th. Okay, and it doesn't matter that previously I parameterized it this way, because once I have my theory and I write it out in this way, all I have to do is now translate between the two. And so you see, for instance, over here, if I wanted to do that that translation, I'd roughly get that alpha effective goes like all sorts of numbers over here, and m pi over f pi to the 10 over 3 halves. Okay, so it didn't matter that I ended up here. So here, for instance, I didn't have 3 vertices that were glued together. It was a direct term in my Lagrangian, but I can always relate the parameters of my theory to the previous effective parametrization that we did to understand how things translate between each other. Okay, and so then let me take this cross section, And now instead of having some relationship between M and alpha effective, I have some relationship between M and the parameters of the theory, let's say M pi over F pi. And so if you go ahead and write down what the solution is for the either fully solving the Boltzmann equation or just using that back of the envelope estimate that we've done in the past. So for instance, if I have here my M pions in GV, and I have over here M pi over F pi, then what we now have obtained, combining what we've done now with what we know the size of this cross section has to be for the simp miracle to work, then we get some curve of how M over F has to behave as a function of M. And so, for instance, over here, going from 10 MeV or so up to a GeV, we get some curve. And also for chiral perturbation theory to sort of be valid, then this M pi over F pi should ballpark be smaller than, let's say, 2 pi, which is somewhere over here. Okay, so this gives us now the parameters of the theory such that that we get the right amount of dark matter. So just to stress, so this is now sort of this is our solution, either directly to the Boltzmann equation or to our freeze-out condition, which we've developed in the past. Okay. So let me give you some references, as I mentioned, for this. So actually, maybe before the references, let me just make sure to state very clearly here. So this is the result that we're finding over here. The fact that we have these 3-to-2 annihilations in this general set of QCD-like theories. This just shows you that you can generally get this. These results are really generic to get simps in QCD-like theories. Okay, so even though these might have seemed like a little bit of an oddball or something a little exotic, there is absolutely nothing exotic about it. Okay, and the mass that we're typically pointed to over here is still of order 100 MeV, of course, depending on the size of the coupling. But that's sort of the general ballpark between an MEV and a GeV scale, the types of masses you should be thinking about for simps. And so now let me give you these references if you want to read a little bit more about the details of this. So this is in a set of papers which I did with collaborators. So this is work together with Kuflik and Hitoshi Murayama and Volansky. And the first paper was also together with Jay Wacker, and a set of work published in PRL 1411.3727. And if you want to include also the dark photon in it, so it's our second paper that was just with Kuflik and Murayama. And that can be found in 1512.07917. So this first paper, the first paper is what we call the simplest miracle. Okay, so this is sort of setting out these pion constructions that give us simp dark matter. And the second paper includes the dark photon. Okay, so hopefully I've been able to show you that that these theories, these different mechanisms, even including ones that may seem a little bit more exotic, are actually completely non-exotic. They just naturally happen in dark sectors in general, and I've demonstrated here a broad class of theories that in which all of these processes can in principle happen. And the next point that I'd like to make is not only are these mechanisms very generic, but they're also very predictive, which of course is something that we care about deeply when we're talking about particle physics. So these ideas are also very predictive. So I want to give you a little bit of a taste of that. Oh, actually, sorry, before talking about them being predictive, let me just actually point out that another way that you could get, I'll just write that over here, another way to get 3-to-2 interactions are to use glue balls. Okay, so so there are a lot of there's some nice works on how you could use glue balls in these theories to get dark glue balls, I should say. So there are other ways to get 3-to-2 interactions, and you can read about this in the Carlson Hall Machekek paper that did the cannibals. in 1992, and there's also some more recent work by Soni and Zhang, and I think this was a work in 2016, and also from a Canadian group, Forstel et al., with other people in 2017. Okay, so that's another way that we could also get 3 to 2s, and glue balls are in general also interesting in these types of theories. Okay, so what do I mean that these theories are predictive? So let's stick with these examples. Oops, these examples that we've been describing, where we understand, we understand all of the different processes that can happen, and so just to show you, so let's write out. We're going to stick to these QCD-like theories. Okay, so a QCD theory with the star Q1 cross the star Q1. Okay, and I remind you, we said then that what I have is my photon. Now kinetically mixes into some dark photon. It's sitting over here. And this is my photon. Okay, and I have some coupling epsilon between them. And so what I can do now is translate, is write down first, let's say if I fix the gauge group and I fix the dark matter mass, and I just look at, I want to look at just one slice of the parameter space to make a point. And I could have sliced it anyway, but let's look, for instance, where I fixed everything except for the size of epsilon and the size of the dark photon mass. Okay? So I'm fixing over here, so this is drawn at fixed gauge group, fixed, fixed m pi, fixed alpha dark, etc. I fixed everything except for the size of the coupling and the mass of the dark photon. And just to show you all sets of different, how the different processes that we discussed sort of lay out in this parameter space. So, so first I have a curve over here. Let me draw this. Whoop. This is the curve of thermalization. Okay. This is the curve where that elastic scattering process is the boundary between thermalized and not thermalized. Okay, and then I also have like ordinary 2 to 2 annihilations, which will look something like this. So this is going to be where two pions annihilate into 2 standard model particles. And you see over here, you can wait, and let me actually just describe what sits where. So, so if I'm basically if I'm along this top curve that I just drew, then that's sort of the ordinary 2 to 2 WIMP-like. Okay, so this is the WIMP-like. If I'm on that curve, this is the WIMP-like dark matter in this parameter space. If I'm along the thermalization curve, that's where I get elders. And in between this WIMP-like and the elder, this is where we have simps. Okay, so in this region over here between them. And so you can actually kind of think of this as similar to, remember we drew yesterday these epsilon min and max values such that the simp mechanism was working. This is sort of translating that into this particular model, seeing how in these particular parameters of the Lagrangian, how things are behaving. And just to note over here that this dip, maybe I'll just, this dip over here happens when the mass of the dark photon is of order twice the dark pion mass. And that's because if you look at this 2 to 2 annihilation, then if my dark photon, which is what's being exchanged there, is exactly twice the dark matter mass, then we're hitting a resonance, and that's why we're seeing this sort of this dip going down here. Okay, and in this regime over here, over here, this is where we get that semi-annihilations contribute also. And maybe I'll just mention though, so down here beneath the elder is where we are not thermalized with the standard model. And so hopefully this gives you already a good sense of the fact that in the simple model that we've written down, different regions of parameter space, depending on the relative size of epsilon and the mass of the dark photon, we simply get different mechanisms, different processes that are controlling the relic abundance of dark matter. Okay, so let's write that down. So different regions of parameter space give us different mechanisms for dark matter. And there are several existing constraints on this parameter space, and also future probes of new experiments or new analyses that could be done that could be probing these different regions of parameter space. So just to sort of mention them, so there are constraints on this parameter space. Okay, and they come from a variety of different different frontiers. So there are some constraints that come from high energy colliders, be it LEP or Tevatron or the LHC or future projections, and also from low energy colliders like Babar and Bell 2. And there also, as I said, there are future probes. Okay, so these are also coming from the high and low energy machines. But there are also future probes from beam dump experiments, beam dump and fixed target. Okay, these are all sorts of different types. So from Apex and SHIP and many other names that you can think to write down here. And there are also, in principle, ways you could hope to probe this parameter space in direct detection through electron recoils. And so, for instance, these days there's Sensei and Super CDMS and many others. And we're going to be talking a lot about direct detection. Actually, our last lesson, our fourth lecture on Friday, will be dedicated to direct detection. But just to sort of mention that all of these exist, and so let me just show you kind of. I don't want to overlay this on the same plot, but let me just reproduce this plot over here. Okay, so here's my epsilon versus MV. And, I have these different something like this, right? This is sort of the way that we had this plot before, and just sort of to show you that generally speaking, we sort of have constraints that are, look something like this. Okay, from all these different existing constraints, roughly it's of order epsilon. You should think of as sort of smaller than 10 to the minus 3 or 10 to the minus 2-ish, depending on the mass, and this is usually changing at a few hundred, let's say 600 MeV. And also over here, there's a jump at 10 GeV in terms of the existing bounds on this parameter space. And then future probes can really hope to probe different regions of parameter space over here. So there are ways, so there's like a lot of work that Bell 2 is going to be able to sort of come in over here, and there beam dump. There's some stuff from SHIP over here, and and high energy colliders operating up here. And so obviously this plot is not meant to be a one-on-one reproduction of a proper plot that you can find in a paper, but sort of roughly to give you that sense that these theories really are predictive. Different regions of parameter space tell us something different about what dark matter mechanism is important. And we have ways to probe these regions of parameter space. And so there should be interesting results coming from all of these different frontiers that really work together to continue to contribute and tell us something about dark matter. But just to sort of roughly if you want to think of it, you need epsilon these days to be smaller, of course, depending on your mass scale, roughly 10 to the minus 3 or 10 to the minus 2, as a function, of course, of the mass of the vector, but over a broad range of its of values. Okay, and there are many future probes. So for my end, that concludes what I wanted to talk about in general for dark sectors. And the next sort of mini piece that I wanted us to discuss today are general constraints. But maybe before I move on, just Luca, let me know if there are any questions on the dark sector part.
Not for the moment. In case I will help you.
Okay, great. So so that's what I wanted to share about these sort of model building efforts or dark sectors in general. Ideas that realize all the mechanisms, showing you that they're generic. All of these mechanisms are generic in theory land and are predictive. And what I'd like to do for the rest of our time today is to give you a little bit of a sense of anytime you write down a new mechanism or you model build for that mechanism and you're trying to sort of work things out, what are the set of constraints that you should sort of hold in your mind so that you make sure that whatever you're doing is okay, is not already ruled out. Okay, so these are sort of general constraints on dark matter parameter space. Okay, and as I said, these are just the sort of things that I want you to keep in mind when you're developing the next amazing dark matter mechanism or model. And of course, these need to be applied to all the ones that should be applied and are applicable to everything that we've been discussing so far, okay? So when you're developing your next mechanism or model, okay? So we're kind of going to go through this, this laundry list, and we're not going to be rigorously deriving each of these bounds. And towards the end, I'll give you also a reference to actually a set of lectures that you can watch if you want to. Well, one particular lecture that I think would be interesting if you want to learn more. If you want to hear a more detailed lecture of how you derive these bounds. But let's get started. So okay, so our first one is going to be sort of a minimal mass bound. Okay, so if you remember in the first lesson, we said that what we know about dark matter is that it has mass, but we have no idea what its mass actually is. So just to give you a few more details about, depending on the nature of dark matter, what and how is a minimal bound that we can set on its mass. And there are actually 3 of these that I'm going to mention. So the first one is going to be, let's call it, so the first one is going to be fuzzy dark matter bound. Okay, so fuzzy dark matter bound. So the fuzzy dark matter bound is just the statement that the de Broglie wavelength of our dark matter has to fit inside the dark matter halos that we're observing. Okay, so so the de Broglie wavelength has to be smaller than the size of galaxies, and in particular the size of the smallest galaxies. So it's actually governed by our dwarf galaxies. Okay, so think of here's my galaxy. Okay, and it has it has some radius and some mass, and my de Broglie wavelength better be contained over there. Otherwise, I wouldn't be observing this halo. Okay, and so the bound that you get from this is that the mass of dark matter has to be larger than around 10 to the minus 22 GeV. Okay, so this is the first bound on the mass, and this bound is true regardless of the nature of dark matter. Okay, we just really always have to be obeying this. So this is true whether your dark matter is a boson or a fermion. Importantly, it's not true if you had, if there are multiple components to dark matter. If there's some subcomponent of dark matter that makes up less than 10% of the total amount of dark matter, then you can evade this bound. Okay, so it's not applicable to a subcomponent. Oops, sub is with a B. Sorry about that. To a subcomponent that has less than 10% of compared to the rest of dark matter. Okay, so that's the first dark matter bound, mass bound. A second one that we can write down is what I'm just going to call phase space packing. So this one is also applicable for fermion dark matter. Okay, so this is for fermion dark matter, and this is sometimes also called the Tremaine gun bound, if you've heard of that. So this is the Tremaine gun bound, and the idea is that Fermi degenerate pressure sets a minimal size for the halo mass. Okay, and so let's just write that out. So Fermi degenerate pressure sets a minimal halo mass. Or maybe said another way, there's a limit, right? Because fermions are fermions, there's a limit on how many fermions I can stuff into a halo. Okay, so there's a limit on how many fermions I can pack into a halo. Okay, that's why it's called phase space packing. And so what you get from this, from working this out, is that the mass of fermionic dark matter should be heavier than around a keV. Some more recent analysis, so there are order ones floating out over here. Recent analysis might push this closer to the 0.1 keV limit, but that's sort of a ballpark of a number that you should keep in mind. Let me just give you actually a reference in case you want to. Recent details you can find in 1311.0282. Okay, so this is some recent details. Oops, in particular, how you get down to here. And so what you can see from here is that this is actually the first way, this is the way in which, the first way that neutrinos, active neutrinos from the standard model were excluded as dark matter, okay, because we know that their mass is beneath a keV. They're certainly fermions. So this already tells us, this bound, that dark matter is not active neutrinos. Okay. And again, listing what type of particles this applies to. So as we said, this one doesn't apply to bosons, but it does apply to fermions. It doesn't, again, apply if I have a subcomponent of dark matter, which is less than 10% of the dark matter abundance. Okay, so it does not apply to a subcomponent that has, ballpark less than 10%. Okay, so that is bound number 2 on the mass. And now let's go to a third bound, which is called warm dark matter, the warm dark matter limit. And here the idea is that if we have, so in general in the early universe, how does structure form? Well, we have, throughout the universe, we have overdensities of dark matter, and structure forms from these initial dark matter overdensities. Okay, so maybe I have, here's my overdensities, a lot of overdensities. Here it's more sparse, and then here there's again a lot of them. And what's going to happen is that structure is kind of going to form, so structure is going to form over here, and structure is going to form over here. Okay, so let's just write that down. Structure forms. So structure forms from dark matter overdensities in the early universe. And what happens is that as this dark matter, I have these overdensities, is that if I have free streaming of dark matter, okay, dark matter is just free streaming through, it's going to wash out structure, and that's going to be potentially an issue. Okay, so free streaming washes out structure. Okay, so if I have some dark matter particle here and it's going to free stream out over here, then what you expect is that I'm going to wash out structure of sizes that are smaller than the free streaming length. Okay, and so basically structure will be suppressed on scales that are smaller than that free streaming length. And so given the size of structure that we see in our universe, this tells us some limitation on the free streaming. The free streaming is, of course, related to mass. And so what this gives us is a bound of dark matter that is, it should be larger than a keV. So for a completely different reason, we reach over here a number that's actually kind of similar to this number that we got beforehand from phase-space packing. Okay, but these are two separate reasons for this bound. So keV is sort of an interesting number in that sense. And if you want to read a little bit more about how you would sort of work through this, you can look at the following paper. It's an Astro paper. It's an Astro PH paper, and the number is 0501562, if you want to read a little bit more. And importantly, this only applies to particles that in the early universe had some velocity, and so they were capable of free streaming. So it does apply to all of the thermal relics that we've been discussing today, and it applies even for some other non-thermal relics. It doesn't apply to bosons that are produced at rest in the early universe, so it's not going to apply for axion dark matter and for dark photon dark matter, which are produced through mixed alignment mechanisms, which we haven't discussed at all in this course, so if you've never heard of them before, that's fine. But in case you have, I just want to mention that it's not applicable to those, okay? So this doesn't apply, so this does apply to thermal. So this applies to thermal relics. Well, it's maybe let's say it more generally. What it doesn't apply to, to bosons that are produced at rest in the early universe. And in particular, it doesn't apply to axions. Okay, and it actually doesn't. It also doesn't apply to, again, to subcomponents that are smaller than ballpark 10%. Okay. So these are three separate constraints for different reasons. They give us bounds in particular cases on what the minimal size of the dark matter mass should be. Let's move on to a different constraint. Let me just see what color I was using up here. Sorry about that. Yeah. Okay, so we finished the minimal, 3 different ways to get a minimal mass bound. And now let's talk about a different bound that's called an effective. Okay, a bound from the effective number of neutrinos in the early universe. And so the idea over here is that, that we get constraints on new relativistic degrees of freedom beyond the standard model. And these things are constrained actually by 2 things. They're constrained by Big Bang nucleosynthesis, which happens when the temperature of the universe is of order 1 MeV and goes down actually till around a keV. And they're also constrained by measurements of the cosmic microwave background, which probes temperatures of order in eV. Okay, so it's constrained by both of these, by measurements that are related to both of these epochs. And so sort of by convention, the convention is that we count how many relativistic degrees of freedom we have in the universe compared or relative to that that's to neutrinos. Okay, so the convention is to count degrees of freedom. So DOF is degrees of freedom relative to the neutrinos. So usually you can think of delta N effective, which is sort of the energy density sitting in relativistic degrees of freedom in the dark sector, normalized to whatever's sitting in the neutrinos, and this is some number, I think it's 4.7, something like that. G star dark, that's the number of degrees of freedom in the dark sector, of relativistic degrees of freedom, times the temperature of the dark sector normalized to the temperature of the neutrinos to the 4th power. Okay, and we have bounds on what the size of this delta N effective is, and actually these days, so we have bounds, as I said, from both BBN and from CMB. The numbers are actually pretty similar these days. So from BBN, it tells us that the contribution to the effective number of neutrinos should be smaller than 0.4. CMB tells us that the same delta N effective at the time of CMB should be smaller than 0.6. So these numbers are actually pretty close. Let me just give you the references in case you want to read more about these. So there's a paper, the first one is 1912.01132, and the second one you can find in 1807.0620. Just point out that even just a few years ago, the BBN bound was actually substantially worse, and so nowadays it's really impressive how there's sort of things have improved, and these bounds from CMB epoch and from BBN are relatively close to each other. And just to point out that actually it's expected from CMB stage 4 data to improve this bound on delta N effective by even a factor of 10 improvement. Okay, so that's something that would be nice. It'll put an even tighter constraint on what we can and can't do in terms of relativistic degrees of freedom in the early universe. And so all of this, what all of this tells us, it tells us a bunch of things, but I want to point out one sort of the point that's relevant for us here is that if you work through sort of, putting in the numbers and what you can find is that if I have, let's say I have some dark sector, okay, so all sorts of dark particles, that have masses that are beneath an MeV, okay? Then what you can show from this constraint on delta N effective is that they must have a temperature, a temperature of these dark sector that is smaller than the temperature of the photons, okay? And so put another way, this tells us that, so if the temperatures are different, that means that these sectors have to be kinetically decoupled. They have to be thermally decoupled. Otherwise, they'd have the same temperature, okay? So this must be kinetically decoupled at an MeV. And so the other way to say this is that if I have a dark sector, dark matter, that's kinetically coupled with the standard model at MeV, then the masses have to be above an MeV. Okay, so if I have some mechanism, let's just write this down. So if I have kinetically coupled, if I'm kinetically coupled at MeV temperatures, then the masses have to be above an MeV. Okay, and so what this tells us is, for instance, so for instance, let's think for a second, for instance, about the SIMP. It's also true for the WIMP. But if I had anything that any process, any mechanism that we worked out that we needed to have kinetic coupling with the standard model, for instance, SIMPs, or we saw we had to dump that entropy. We had to be kinetically coupled with the standard model at the time of freeze out. Then the masses have to be above an MeV. Otherwise, we're going to be in trouble with BBN. Okay, so for instance, what this tells us for SIMPs. Okay, and this is just an example. So it sets a bound in the SIMP case, and also for others. Okay, that if I have to be kinetically coupled, then my mass better be larger than MeV. Okay, and that's why when we discussed SIMP earlier, I was saying that sort of the mass range to keep in mind is between around an MeV to a GeV. We can't really go beneath an MeV because we're going to get in trouble with extra degrees of freedom that are going to mess things up in the early universe. So that's a bound from N effective. Let's move on to another bound, self-scattering. So self-scattering or self-interactions. Okay, and as we actually mentioned already in the first lesson, I said that dark matter can't too strongly self-interact or strongly self-scatter because these strong interactions can distort dynamics in dark matter halos. Okay, so the idea is here we have to worry about distorting dynamics in dark matter halos. And so the idea is here, what I mean is here's my self-scattering. I have two chi's that scatter into another two chi's. They're bumping into each other, and stuff is going to start changing. And so we have bounds from, for instance, the bullet cluster and from halo shapes. And these, what these tell us is the way that this bound is usually phrased is that if I have some cross section for this self-scattering process, so I have some cross section for the self-scattering, okay, normalized by the mass of the dark matter particle, this should typically be smaller than around 1 centimeter squared per gram. Okay, and the truth is that there's some. This number isn't exact. First of all, it's what this number should be changes somewhat depending on the system that you're looking at and what its velocity is. So really, there's some sort of spread. This number 1 centimeter squared per gram, depending on the velocity of the system, this number 1 sort of ranges from an order of magnitude lower, an order of magnitude larger. But this is sort of the typical ballpark that you should keep in mind. Okay. So on the one hand, this is a constraint on the size of this self-interaction cross section. And I'll also just mention that there are some long-standing puzzles in structure formation that have been about for a while, and it's possible that these puzzles can be addressed by having a self-scattering cross-section that's very close to this bound, close to that limiting value. So we have long-standing puzzles in structure formation. So I'll give you the names in case you ever hear of them. So one is called core versus cusp, and the other one is called too big to fail. And so just sort of generally, core versus cusp is the statement that if we had collisionless dark matter that didn't have any self-scatterings, then it would predict dark matter halos that are sort of cuspy towards the center. So, like the density goes up, and observationally they're flatter. And too big to fail is just a statement that there's a mismatch between, the brightest stars and between the biggest stars and the brightest satellites. So these are sort of puzzles that have been around for a while in structure formation. I use the word puzzles. They're not really problems because it's very possible. There's a lot of debate within the astrophysics community about it could be that these issues would be solved with unaccounted for baryonic effects, for instance, within sort of these simulations that give these predictions. But what I just want to stress here from the particle physics point of view is that so these could be addressed, or it's possible that these issues. So I just want to make clear these aren't problems; these are puzzles. It's possible that could be addressed by astrophysics. All sorts of things that haven't been taken into account properly, including certain baryonic effects. But it's also been shown that if you have strong self-interactions, that could be something that could assist in resolving these puzzles, okay? So it's also been shown that self-interactions that are of order exactly this 1 centimeter squared per gram could assist, okay? And this number, by the way, sort of in particle physics units, this is around 100 barn per MeV. Okay, so this is really a strong scale cross-section, strong scale interactions. Okay, and if you want to read a little bit more about the particle physics side of this, there's a nice review on the topic by Sean Tulin and Haibo Yu, and it's in 1705.02358. There's a nice review of this topic. And so just to show you that what this means for SIMPs, so which was the case that we had these strong interactions thus far. So for instance, what would this tell us about SIMPs? Okay, and this should of course be true always. Every model always has to obey this bound. But I just want to show you that SIMPs are sort of a little extra sensitive to this, because if you'd expect that if I have some theory that has strong 3-to-2 annihilations, you would just expect that theory would also have strong 2-to-2 self-scatterings. Okay, so you'd expect that if you have generically, that if you have strong 3-to-2s, that you'd also generically get strong 2-to-2s, self-scatterings. Okay? Sorry, that was extraordinarily bad handwriting on my part. I apologize. Okay? And so you can both think of this as something that's, a constraint on your theory, but also sort of a possible signal, or something that's a feature because it can kind of assist in these puzzles. Okay? And so what I want to do right now is just to sort of go back to that parameter space in our pion construction of the SIMP mechanism, where we had this plot where we showed, okay, here's my pion mass, my dark pion, and I have over here m pi over f pi. So we're now looking at a particular model where we can, and as we said, I can now show what's my solution to the relic abundance, which is a function of these parameters, right? So this is our solution that we drew before, solution to the relic abundance. Okay, and I showed you before that there's some, right? We said there's some. Let's say I can't go too high over here because I want to have a perturbative theory. So I can't go too high in terms of m pi over f pi. What I want to show you is that what I can do is, these theories that predict very particular Lagrangian that gives me 5-point interactions, there are also 2 to 2, also 4-point interactions, so 2 to 2 self-scatterings, and you can work out what those terms are in this particular theory. And then along your solution to the Boltzmann equation, along your solution to the relic abundance, see where do we saturate the bound from self-scattering? Okay, so that's a constraint on our parameter space. And when you work this out, here's the result that you get. You find that so there's some curve. Whoops, that's going to be down here. So this is going to be the curve of where I'm setting the sigma of the self-scattering over mass to be smaller than this 1 centimeter squared per gram bound. Okay? And so you see combined what happens over here. Let's look at the total viability of this theory. So I end up with a lower bound on my mass as well as an upper bound on my mass. Okay? And so I'm pointed to some mass range over here in which everything is working. Okay, there's some viable range over here for dark matter, and this range typically sits that your dark matter is of order a few hundreds of MeV. And so combining both the 3 to 2 annihilations as well as constraints from self-scatterings gives us further constraints on the parameter space of these pion theories, and really points us to a very particular mass range such that everything is really viable for this dark matter mechanism. And I've shown you how this works, what this works for SIMPs. I'll just also mention that you can also be compatible with large, well, you can also get, sorry, oops. You can also get large self-interactions or self-scatterings that can be relevant to address these puzzles with forbidden dark matter. Okay, you don't get it for WIMPs and for many of the other mechanisms, but for SIMPs and for forbidden, this is something that can work.
You need a question on the plot.
Mm-hmm. Yeah.
So the area that is allowed from the bound of the cross-section over the mass, smaller than 1 centimeter square over G, is on the left-hand side of the green line. Is that correct?
Mm-hmm. Yeah. So the green line is showing you along the solution for the relic abundance, along the values of the black curve. It's showing you where is sigma over m equals a centimeter squared per gram, and then you have to be below that curve.
Okay, so the upper bound of the mass that you pointed out for the mass of the pion shouldn't be the upper bound shouldn't be the crossing between the black line and the green line. No,
so the upper bound is coming. So you see okay, so this is maybe whoops, of course I see why this is confusing. It's like so the green line is, think of it as like a separate plot that I'm just overlaying, okay? The green line is telling me I have to be smaller. This is a value of sigma, so I basically have to be any mass that's below, oops, sorry, let me do this in a different color, okay? So conceptually I have to be below this green curve, okay? And the green curve isn't showing you the value of m over f. It's showing you along the black curve, what is the value of sigma over m, okay? And the only reason that so this gives me only a lower limit on what the mass can be, because once I go to a regime where I'm above 2 pi, then I'm in trouble, okay? So as long as I'm beneath 2 pi, I'm fine.
Okay.
So it's just showing, okay?
Okay, so it means that on the epsilon axis for the green band, there is not the mass of the pi over f pi. It's not epsilon.
It's as a function, exactly. It's m pi. It's just showing you what the sigma is along the black curve.
Okay, perfect.
Yeah.
That's clear. Thank you.
So yeah, so when you combine this, what you know about chiral, that you don't want your theory to be, you want to be able for things to be calculable. There's a rough upper bound. You can't say exactly where it is because that's where the coupling becomes strong, and you know that there are order ones that you haven't been able to account for because your theory is no longer perturbative. But from the lower bound, you just have 2 large annihilation cross sections, and you're just not okay. Self scatterings, excuse me. Okay.
Okay, perfect.
Okay. And so we just have one more type of bound to complete in the next few minutes, and these is bounds that I'll call indirect detection. And so indirect detection, the idea is that we look to the sky, and we can in principle see all sorts of standard model particles that are being produced and coming at us that we can see that are coming from either annihilations or decays or some type of interactions from dark matter happening up there. So maybe dark matter is is annihilating these days into standard model particles, or maybe there's some sort of late time, very slow decays that happen once in a while, etc. And so we look to the sky. Obviously, we don't do that with our naked eye. We do that with very fancy telescopes and satellites. And we hope to see, and we do indeed see, either annihilation or decay products. So these might be, maybe these are photons or positrons or electrons, or any other particle that you can think of that are sourced by dark matter interactions. Or said another way, we look at what we observe, and then we say, okay, what does this tell me? What kind of bound does this put on what dark matter could be doing, such that I've measured this flux, or that I've seen these particles at these energies. Okay, and so for instance, like I can have, so there's some there are all sorts of measurements over a broad range of energy. So let's say for some photon spectrum in MeV units, and there's some flux of particles, and in the measurements there are different experiments, really over a broad range of energies. So over here, this is, let's say, from a keV scale up to 10 to the 4th. Okay, so spanning a very broad range, and also over here in terms of the size of flux, there are many different observations. And so in principle, what it does is it sets bounds on late times, annihilations, and decays. We likewise also have constraints that come from energy injection to the CMB. And actually, all of these bounds, there's a really nice review, specifically on indirect detection. There's a set of TASI notes by Tracy Slater, and you can find it on the archive. It's 1710.05137. And what are the exact bounds on a decay rate or on an annihilation cross-section is very strongly dependent both on the mass of the particle and the final state, and things like that. But at least sort of if there's one number that you can sort of, you want to take away from this, let's say for decaying dark matter, I'll just mention this one, that let's say for decaying dark matter, again, depending on the final state and all of this stuff, you'll find that the lifetime of the particle should be larger than somewhere between 10 to the 24 and 10 to the 28 seconds. Okay, and so sort of if you were, well, this is sort of again as a function of mass, but if sort of moving forward, if you ever need to sort of do a quick back of the envelope estimate, a good starting point is to kind of take lifetimes of 10 to the minus 20, sorry, not minus, of course, 10 to the plus 27 seconds. Okay. And of course, this is just important to note. This is much longer than the age. You normally think, well, I need my dark matter to be stable, so my bound should be the age of the universe. The age of the universe, T universe, is of course close to 40 billion years, and that's roughly 4 times 10 to the 17 seconds. So the bounds that we have on from decays and things like that are actually much stronger than just saying it needs to be stable. And again, for further details, I recommend reading these TASI notes on indirect detection. And just to bring today's lesson to a conclusion, the last type of constraint or hope that we could method for detection is direct detection, and this is really going to be the focus of our last lecture on Friday, and we're talking about this less from the prospect of the bounds that it sets, and trying to really share with you what is direct detection and what are all the really exciting new ideas, technologies, materials that people have been thinking about for how we could hope to detect dark matter in the lab. Okay, so this is how we would detect dark matter in the lab. Okay, so that's it for me for today. Thanks so much for listening.
Thanks to you.
Any questions?
And connecting to a question of the student, and given the increasing interest on actions, Could you comment on which bounds are more relevant for actions as dark matter?
Yeah, the only one that we've derived, the only one that really that's relevant that we've derived right now today. Well, I'm not going to scroll all the way back there. Was the mass bound, the first one, the fuzzy dark matter. So that sort of ballpark of 10 to the minus 22. Really, when people think of axions, although in principle it could be a dark matter candidate over a very, very broad range of masses. When we think about what is, let me say this differently. In the first lesson, we sort of spanned these 80 orders of magnitude of masses that dark matter can sit in. Most of the mechanisms that we've discussed over here, you see, I'm thinking of dark matter as a particle. And that typically means that I'm really thinking of it as sort of above a milli eV in mass. When it's lighter than that, it makes more sense to start thinking about it as a field. That also really governs the way that we think about how to produce it in the early universe, as well as how we could hope to detect it in the lab. So really, from the axion perspective, it's usually produced by very different types of mechanisms in the early universe that are called misalignment mechanisms. And for the most part, the bound that's really the bound that's most relevant is the minimal mass bound from fuzzy dark matter. Of course, if I have an axion in a particular mass range, and I could have axions that couple to photons, and then they can produce, they could produce indirect detection signals, and there's definitely signals and bounds that could happen from that. But that's a slightly different category of type of particle and mass ranges than we've been mostly focused on in these lectures.
Okay, and a very last question about the dark sector: are there bounds that come from neutrino experiments as well for dark photon theories?
What was as well as what? What was the second one?
As well for dark photon theories.
Yeah, there definitely are. I'd say that most of the depending on the particular theory that you wrote. So dark photon, maybe I'll start differently. Dark photons are certainly, whether thought of as mediators or as the dark matter themselves, or something that's sort of independent of the question of dark matter, just as something that could exist and how could we detect it. It's definitely something that's been thought of a lot, and there are many interesting constraints and projections, specifically from neutrino experiments. I'd have to check. I'm not off the top of my head. I'm not certain. I don't have like a plot that's a plot or a projection that's coming to mind. But definitely, I mean, dark photons sort of stand without the context of dark matter, or without the context of a particular dark matter mechanism, as something that's been very, very heavily studied. Many new machines are being thought up and being proposed, and hopefully will be funded and come into construction, that are aimed at tackling different regions of their parameter space. Over here, what I've tried to do is really link these dark photons a little bit more to the context of dark matter, because they're something that could really naturally be sitting in any of these dark sectors.
Okay, thanks a lot. If there are no other questions, thanks a lot, Ionit, for this class. Remember that tomorrow there will be the tutoring lecture, and on Friday again we will have the last theory class. So thank everybody, and see you tomorrow at 10.